recording, it would be better if I changed the input. Let's see, there we go. All right, a couple of things that have nothing to do with statics. First off, we did expand the enrollment caps for dynamics and deformable bodies next semester, so did everybody get in that needed it? Good. What else was I going to say? Oh, if we need to, we can expand it further, so don't worry. If it comes down to it, Corbly 105 is open, and it has 150 seats, so we'll move it in there. So don't worry. Everybody needs to take it. We'll take it. Okay, we got a little bit of headway done on grading. All of the homework 5s are graded. The homework 6 is 6.1 to 6.3 are still being graded, but today I have assigned homework 7. It is not due until December 1st. This is our last homework, so if you're okay with that. I do have some room for some bonus points later on during dead week, but nothing in the way of, like there's no gargantuan amount of work. And this is a very short assignment. And let me say a couple things about this assignment. There is one parameter regarding our final topic in the course, which is friction, which I am not talking about today. That parameter is dealing with the trig. That being said, if you're feeling comfortable with the trig, you could probably do this homework now, although it's not on exam 3. Speaking of exam 3, I started a thread on Teams for you to collate questions for the exam. I was looking through my notes. Last year, we ended up doing a truss problem together. That's what we did last year during the 3rd exam review. So it doesn't matter. We can do a shear and moment problem, we can do a truss problem, we can do a centroid, we can, whatever. Just come prepared, ready for questions. Okay. Today, what I'm going to do is hopefully do, admittedly, a little bit of a better job than I did last year. Friction was rushed last year, and it's not a challenging concept if you understand some of the basic parameters, which is what we're going to be talking about today. So today is more about the concepts involving friction, and when we come back from break, we'll do maybe slightly more rigorous problems involving friction. And I say slightly because really the only thing I'm adding is trig. So let's talk a little bit about friction. It is our last topic in this course. And I'll go ahead and tell you that if you go through the textbook, there are some things that I didn't cover. For instance, I did not cover statics of frames or machines, and that is sometimes a popular topic in this course. But what I wanted to do when I developed my outline for this class is I wanted to cover truly stuff that was like unique and standalone type topics. Like, for example, frames and machines is just combining a lot of the other stuff we've already talked about in here, so there's nothing really new there. But friction's a little new. And it is going to pop up in various disciplines, whether you're civil, mechanical, biomedical, etc. So I think it deserves its time in the spotlight. Friction comes from two objects in direct contact with one another, okay? And what happens is, so consider like this. I've got a block on the ground, okay? What's happening? So first off, let's consider just this situation over here on the left. Let's just consider this, okay? There's not a lot going on here, or at least deceptively, there's not a lot going on here, but I want to illustrate what's going on from a statics perspective. So we have the weight of the box, which is acting downward, and so the box is sitting still. It's not going anywhere. So what that means is something has to be pushing upwards, right? Because the sum of the forces along the y direction must be equal to 0. I propose that they are. What's happening is that the floor is pushing back up, and it is pushing back with a force normal to the floor, perpendicular, if you will, in all directions. Remember, there's vectors normal to the plane, right? So I am calling that the normal force. Now, in this case, the magnitude of those two forces are equal to one another. That's not necessarily the case all of the time, so that's why I'm using different letters. But I propose that the magnitude of N and the magnitude of W are the exact same. Now, imagine I take this box and I start shoving it laterally. I apply a lateral load P. I propose that the floor resists that through a frictional interaction between the box and the floor. Here's a table. If I take this table, so let's look at this table. All right, this table has a weight that is acting downwards. It's not moving anywhere because the floor is pushing back upwards. It is holding this table right where it is. Now, if I take this table and I push, all right, there is a point where if I apply enough force, it will begin to move. But if I just push it a little bit, like let's just take it and push it a little bit, it's not moving, right? Here I am pushing it, it's not moving. Why is it not moving? Well, it's not moving because there is a force resisting it in the opposite direction. What is that force? It is a frictional force developed between the table and the floor. Now, how many of you have ever helped a friend move furniture, or you've moved a couch, in your house or anything like that? How many of you ever moved stuff across the floor ever in your life? Just about everybody has. Okay. One of the things about friction is that there are two types of friction that we encounter. There is static friction and there is kinetic friction. Static friction is the force developed that impedes motion, that prevents motion from occurring. And then kinetic friction is the force that's developed during motion. And whatever happens with friction, one of the things that is always true is that the kinetic friction is less than the static friction. In other words, if I've got this table, it is easier to keep the table moving than it is to get it to start moving, right? Once you get it started moving, it's a lot easier to keep it moving than it is to get it started back up again, right? If you've ever been with a friend or a family member or whatnot, you're moving furniture, you've got some really heavy couch or something, get it moving. It's easier to keep it moving than it is to get it to start moving. Has anybody ever experienced that before? I think probably most of you have. Okay? Now, problems involving friction are concerned with two objects in contact and trying to quantify the frictional force between those two objects, okay? Or, more specifically, how much force is required for motion to begin, okay? Which I think would be of concern to us in this course, considering that the whole focus of this course are objects and components in static equilibrium. So we're trying to see when motion occurs or not. So I propose that there are two fundamental forces that we can compute at the beginning of any statics problem, and that is the force required to begin motion and the force generated during motion. So the force required to begin motion, which I'm calling F sub m, is computed by taking the coefficient of static friction, which I'll talk about these coefficients here in a little bit, times the normal force between the two objects. So, for example, and just to give you some concept along with this normal force, it is a whole lot easier for me to push this table across the floor than it would be if three of you were sitting on the table, because it would increase the force between the table and the floor. Increasing the force between the table and the floor would increase the amount of force required to begin motion, because the force required to begin motion is a function of that normal force. Okay? Now, the force generated during motion is likewise the normal force multiplied by a coefficient of kinetic friction. So there's a coefficient of static friction and a coefficient of kinetic friction. Now, probably the most singular important concept about friction, and it's one of the magical things about friction in any statics problem or any physics problem. The key takeaway with friction problems is that friction is developed to resist motion. Okay? And what I mean by that is this. I am here on this side of the table. Here's the table. I'm going to push the table this way. Which way is the friction acting? This way, right? It acts to impede motion. If I walk over here and I push, which way is the friction acting? This way, okay? Friction always acts to impede motion, okay? That is an incredibly important point to recognize. And if you recognize that when you draw your free body diagrams, 99% of the problems are going to go away. Now, let's talk about these coefficients of friction. There are two coefficients of friction that can be developed between two surfaces, the coefficient of static friction and the coefficient of kinetic friction. So these are very easy to determine experimentally. Basically, all you're doing is taking two objects with known material properties, sticking them sticking them next to one another, applying a known normal force between them, and then applying that tangential force and seeing when motion starts. Excuse me. So approximate values for coefficients of friction are pretty easy to look up. And I think that the concept hopefully makes sense. For instance, the friction developed between metal-on-metal contact would conceivably be different than the friction developed between metal-on-leather or stone-on-stone or wood-on-wood or rubber-on-concrete, etc. And some of these values are very, very critical to engineering applications beyond just Engineering 213. I would imagine that there's a number of engineers in this room that would be very interested to understand the coefficient of friction between rubber and concrete. Why is that? Boom, tires, right? We need to understand the friction that's developed between tires and the road surface to understand braking distances, to understand forces developed in the wheel assembly, and so on and so forth. Understanding those frictional relationships is critical to what we do as engineers in a variety of disciplines. So I don't want anybody to think, oh, this is just the mechanical topic or the civil topic. Now, this is an important topic across the board. Now, one of the things that I mentioned earlier is I said that, if you're moving something really heavy, if your buddy wants you to get together and move a fridge or a couch or something, I said that, one of the things that you'll find is it's easier to get it or to keep it moving than it is to get it to start moving. Numerically, what that always means is that the coefficient of static friction is generally always higher than the coefficient of kinetic friction, okay? Specifically, this is a rule of thumb. The coefficient of kinetic friction is usually about 75% of the coefficient of static friction. I'm not saying that's always the case, but you can maybe kind of hang your hat on something like that. So, for example, if I have a coefficient of static friction of 0.3, maybe my coefficient of kinetic friction is like, I don't know, 0.22, 0.2, something like that. It's not, a hard and fast rule, but it's kind of an idea that you can use to quantify your results. All right. Now, one thing that we are not going to deal with today is the trig components of this exercise. So we're not going to deal with the inclined component of this surface. But the one thing I want you to recognize conceptually is that the normal force is the force developed between the two objects. The point being, so for example, let me just look at this concept here, because I think that while we're not going to deal with the trig, and I'm not going to ask you to get into the weeds of sines and cosines and all of that, I want you to recognize that, for example, if all that this problem had was a box with a weight W, W acts downward. W acts vertically with the direction of gravity, okay? So if I take this W and I ask myself how much of, there's Yoshi. I'll talk about Yoshi here in a second. Here's W, right? That W, if I take W and use a little bit of trig, some of that W is going to be acting parallel to this plane, sort of, tending it to slide down the ramp, and some of that W is acting normal to this surface. So with a little bit of trig, I can probably determine how much of this W is acting normal to the plane. Similarly with this P force, right? The P force, I can take this and split into X and Y components. What I am interested in terms of friction is the force normal to the plane, okay? So later on, when we do some problems with a little bit of incline, you gotta pay attention to those angles and pay attention to that trig. That's not gonna be a problem today, but it'll be a problem when we come back. But does everybody kind of get the idea of what I'm talking about? Okay. Now here's my example for today. There's Yoshi, our favorite Jurassic means of transportation, especially for certain groups of Italian plumbers. We have a box here on a surface, okay? So here's the floor, and I have a crate here that has a mass of 50 kilograms, okay? Now, attached to this crate, we got this cable here, and it's suspended downward. I have a force of 100 newtons. So what do we think this force of 100 newtons is going to do? It's going to pull the box this way, right? That should be pretty simple. Now, we got Yoshi over here. Yoshi's standing by, ready to either push the crate or pull the crate. What we're going to be interested in with the series of these questions I'm going to ask you is this term F sub F. I want to know how much friction is developed between these surfaces, okay? And the math on these problems are going to be really easy, okay? I don't want you to think that the math is going to be very difficult. We got a 50 kilogram crate, 100 Newton weight. Here are our coefficients of static and kinetic friction respectively. What we're going to do for this problem is ask a series of questions, and we're going to see if we all understand what's going on with this. So here are the questions, and we'll tackle them one at a time, but here are the questions. So number one, will the crate move on its own? If not, or maybe even if so, what is F sub F? Number two, how much force does Yoshi need to use to push the crate into motion? I get it moving this way. Or how much force does Yoshi need to use to pull the crate into motion the other way? Fourth, if this increases to 200 newtons, what is the friction developed between the surfaces? And finally, if this force increases to 200 newtons, how much weight do I need to stack on top of that crate to prevent motion? So the way that the questions are worded, you can probably guess what's going on with 1 and 4. But we'll see what happens when we go through the math, because I think the math is kind of important. Does that make sense? All right, let's see how much work Yoshi's going to have to do. No, I don't want the annotations. All right, you all been in this class for quite some time. Anybody see a problem with this number right here that we need to deal with right now? That's a mass, not a weight. You are exactly right. We need to compute the weight of this box. So that is 490.5 newtons. Now, this is going to seem very nitpicky, but if the weight is 490.5 newtons, what is the normal force in this situation? It's not. I'm not trying to ask you a trick question, but you'll understand why I'm being nitpicky here. It's just the weight, right? In other words, if here's a box and it has a weight, and here's the floor responds with a normal force, N equals W. Right? Does that make sense? Okay, now, the reason I'm being kind of nitpicky on this, and you'll understand why, is when we get to question 5. You'll go, okay, now I get what he was talking about. So just bear with me. So far, so good? Now, if this is my normal force, how do I determine the force required to begin motion? What do I do? I take the normal force and I multiply it by what? Coefficient of, I'll give you a hint. Is it the coefficient of static friction or the coefficient of kinetic friction? There we go, okay. So that is 0.25 times 490.5. And I'll go ahead and do this math for you. When you chug this out, you'll get 122.625 newtons. And similarly, the force developed during that motion is this, or 98.1 newtons. Okay. Is everybody with me on this math so far? Okay. Now, if you are with me, I want an answer to this first question. Will the crate move on its own? What do you think? Yes. Okay, why? Well, okay, hold on. Let's talk about that. So let's look at the crate. Okay? Here's the crate. And the crate, first off, that 100 Newton force, what's it doing to the crate? It's really yanking it this way, right? Now, how much force is required to begin motion? 122. So, is the crate going to move on its own? No, yeah, okay. There you go. That's a fair point. So, will the crate move on its own? No. All right? That is a big old no. Okay? If it has not moved on its own, how much friction is developed between the crate and the floor? What is F sub F? What do you think? What would the principles of statics tell you? All right, let's talk about that. So you're saying this is 122.625? Okay, let's live in that universe. How much force do I have going to the right? 100 newtons? How much force do I have going to the left? 122.625? I thought we said the box wasn't in motion. It'd be 100, right? Let me give you the analogy. Let's live in a universe where it takes 20 pounds to move this thing over to the left. Now, if I push it with 3 pounds, it's not moving. How much force is the friction, how much force is developed in friction between the table and the floor if I push it with 3 pounds this way? 3 pounds. Does that make sense? So I can keep developing that force until I get to 122.625, then it'll start moving. Does that make sense? Is everybody okay with that? So I propose from a sum of forces in the x direction equals 0 perspective, it's just 100 newtons. See, before we start moving on to other questions, this is the stuff I want to make sure it makes sense, right? It's not the math that's hard. The math is easy. It's the concepts. This whole lecture is about concepts involving friction. Does this make sense? Okay, if this makes sense, I think that the next question will be very easy. How much force does Yoshi need to use to push the crate in motion to the right? So here's the image of Yoshi standing next to the crate, and to get that crate moving to the right, how much force does Yoshi need to use? What? That's exactly right. That's exactly right. Let's look at our free body diagram to clarify that. So here's the crate. We've got 100 newtons, right? We've got Yoshi pushing on it, right? And what's going to resist it in this case is Fm, right? Because the idea is, first off, the friction is going to oppose the intended motion. If the motion we're intending is to the right, friction is acting to the left. And we're talking about the force required to push the crate into motion. We got to overcome F sub m to get the crate into motion. And F sub m is 122.625. So if I sum forces in the x direction, I get F Yoshi plus 100 minus 122.625 is 0. And so F Yoshi is, hold on, any excuse to throw video game characters into a lecture. What do we think? Does this make sense? Just wait. Just wait. Okay? Now I'm going to ask a different question. First off, is everybody okay with question 2? All right? Question 3. How much force does Yoshi need to use to pull the crate into motion? All right, hold on. We got to see how much Yoshi's got to effort here. So here's the crate. So here's the crate. The crate has a 100 Newton force right here, but in this case, Yoshi is going to be pulling this way, right? And if the intent is to start motion this way, which way is friction acting? To the right. So how much does Yoshi need to pull to get that crate to move to the left? 222.625. That's exactly right. Because if I sum forces in the x direction, What do we think?
I think Yoshi's ripped. Yoshi's in the gym constantly. Shredded.
That has nothing to do with statics. I wonder what our speaker outside would have to say about that. I don't know why I thought of that. Okay. It's Friday. I'm allowed to tell a joke every now and then. Okay. Let me stop for a sec, though, and ask if everybody's okay with this. Because I'm about to I don't want to say ratchet it up in difficulty, but I am going to ratchet it up in conceptual understanding. Now, this question right here, I really want to pay attention to this and make sure that everybody's really understanding it. Now, for the next two questions, because I guess Yoshi's been put through the ringer, Yoshi's going to go off to, the Mushroom Kingdom or whatnot. Yoshi's gone for the next couple questions. So no Yoshi. If the 100 Newton force increased to 200 Newtons, what is F sub F? Okay? And it is worded a very specific way because I want to make sure that everybody's okay with this. Now, so now we have, instead of 100 newtons, so let me write 100 newtons and say no. That's 200 newtons. Now, 200 newtons is yanking this way. I'm developing a frictional force this way. I'm going to ask a different question about this. Is the box moving? Why? Why is the box moving? Okay, that's 100% right. We have exceeded the force required to begin motion. But that doesn't answer the question. So let me write that. How about this? 200 newtons is greater than or equal to Fm. Motion occurs. What is FF? That's exactly right. The friction is Fk. Oh, I crossed through the question. Because the box is now moving, the friction developed is a constant Fk. Remember what I said. Once the box is moving, okay, we're in kinetic friction land. It's easier to keep the box moving than it is to get the box to start moving. But in this case, motion is happening. So the friction is just 98.1 newtons. That's important, and I really want to make sure that makes sense. Is everybody okay with that? Now the last question. If the 100 Newton force increased to 200 newtons, how much weight would need to be stacked on top of the crate to prevent motion? Okay, now let's think about this one. So here's the crate. Let's draw the floor on here. Okay? Now, the crate has a weight that's acting downward. Is that a fair statement? And then on top of this, we're going to add some new weight. Let's give it another letter. Let's call that P. Okay? Now I'm yanking on this with 200 newtons. Okay? So what's going on down here? Well, first off, if I'm yanking this way, I have a frictional force developed this way. Now, we're talking about how much weight would need to be stacked on top of the crate to prevent motion. So we're trying to figure out this. But we already know that, don't we? Well, not really with this problem. How did we compute this? What was the formula for that? Say it again. What's the problem with that? What's in this case? Boom. That's exactly right. We have a new normal force. So let's talk about that. Let's see. How do we want to do this? So let's start off with let's sum forces in the y direction. So we'll say minus P. What was W? What was the weight of the box? No, that's the mass of the box. What's the weight of the box? All right, everybody okay with this? So N equals P plus 490.5 newtons. So let's just keep that in mind. Now, if I sum forces in the x direction, what do I have? I have negative Fm plus 200 newtons equals 0. Fm has got to be 200 newtons, which, now hold on, I don't think that's all that confusing, right? If I'm yanking on the box with 200 newtons this way, and I'm trying to figure out how to prevent motion, well, the floor, that frictional force developed between the crate and the floor, better be 200 newtons, right? If I push 200 newtons this way, it better resist with 200 newtons that way so the box doesn't move. Make sense? But here's the thing. Fm, see, before we said Fm was like 122.625, but we computed that based on the weight of the box alone, okay? Here's the thing. Fm is 200 newtons, but the way we compute that is mu s times n. So 200 newtons is mu s, which is 0.25, times n. And n in this case is P plus 490.5. So dividing both sides by 0.25, 800 newtons is P plus 490.5 newtons. So therefore, we have that. What do you think? Is that, does that make sense? This is a concept question. Like, hopefully the math isn't the tough part. Are there any questions about these examples, like the concepts? Everybody good? All right, hold on, just a couple things. So Monday, we've got our exam review. Be prepared to ask questions about the exam. Wednesday, we have our exam. Friday, no class. Now listen, I'm assigning your final friction assignment today. You probably will not, I mean, you could do it today. I'm not saying nothing's going to stop you. It's just the problem involves an incline. If you want to go ahead and attack it, go right ahead. But if not, when we come back from break, we are talking about the trig specifically. So that's okay. I'll leave you 8 minutes early to go enjoy the festivities outside. That's all I have. You all have a wonderful weekend.